Oh, hi. This is 971 Vision. My name is Charlie.
My name is Alex. Okay, so I'm gonna start off. I'm gonna go through like the hardware stuff on the Orins, which is our vision system, and then he'll start talking about software, which is gonna take up most of the presentation. Okay, for starting up, we have our old stack. This is what we used to use to interface with our Orins. We had two separate boards, this one and this one. Our bottom board would basically break out CAN from the Orin via an interface board, which was this guy right here. And then we also had two MIPI to HDMI converters on it, which are these little parts right here. And then we also had a fan controller, which is on the bottom right here. And then a DC to DC converter, which was this part up here leading to here. So this would do a lot of stuff. Mostly, the most important part was the MIPI to HDMI and then the power conversion. I'll talk more later in the presentation about the fan controller. And then I'd never really mention it later on, but we basically don't use CAN. After these revisions, we stopped just using CAN. For the top board, we call it the indicator board. So we had 9 dual color indicating LEDs. We had red and green. A couple of them were power and stuff like that, but most of them were connected to GPIO pins on the 40-pin header, which this would interface with this 40-pin header. So these two would go on top of each other, and this one would go under the main board. We also had a serial port on top, which would connect to this. There's like a 10-pin header back here. You kind of can't really see it. But we had a serial port that would connect to it via a 6-pin multi-cell right here. Charlie can talk more about why we need serial.
So just in case when we lose like comms to the Orin, we can manually connect into the Orin with the serial port and manually change the IP and subnet mask on the Orin through serial. So it's like a contingency plan if the Orin somehow can't talk to us with Ethernet.
Yeah. So we've never really used serial on this board in particular. We're just now starting to develop using serial. So this was never really put into play, but in the new revision, we actually kept it, and then we're going to start using it now. We also had 2 buttons for reset and boot. It's going to be these 2 guys right here. We use these a lot because essentially what they do is they short a couple pins in this 10-pin header back here. Buttons were probably one of the best features, one of the 3 main features on like these 2 boards. And then more CAN broken out. I think this CAN was from the 40-pin header, if I'm not mistaken. If not, it's from this 4-pin header back here. Okay, we also had multiple revisions of both boards. I believe this is a V2. Maybe it's a V3. I'm not really sure. And then this for sure is a V3. We had multiple versions. Every single time, we basically kept the same package, but we would add new features. For example, this fan controller wasn't in till probably version 2. And then, yeah, over here, I think this is actually version 1. Version 2, I'm not sure. I don't think we ended up ever producing it. Either way, okay. Our new stack, we basically only have one board. So it's this top board. It kind of has the same design, or not design, but has the same profile as this guy right here. It just contains everything that we basically need. So most important thing is the DC to DC converter. This basically gives our Orin stable power. Our Orin can run off of 12 volts. However, we found that when we do that, sometimes it cuts power. It's just generally not that great. So for like a part of the PCB this small, it's generally worth it for us to give it a stable 18 volts. We designed it to handle 3 amps, for the Orin to pull 3 amps, but I'm pretty sure it can pull a lot more than that. Our 3 buttons are these guys right here. I added one more. I added sleep as per request of some people on the software team. Also kept the 2 MIPI to HDMI converters. We really like our HDMI cameras, or actually they're MIPI cameras, but we run them through HDMI because essentially when we were running them through MIPI, we had a lot of scenarios in which the MIPI cable would get frayed or the pins would separate from the actual plastic. And these are like super fragile, so we like to keep them inside of the actual case and just limit them as much as possible to like the outside world. So we kept them right here. It's at a 90-degree angle now, which is kind of different compared to this one right here, which you can see they're very close, but at a straight angle. Next thing, we had an RF cage for a switching converter. This guy right here, we ran into signal integrity issues in our previous board designs. So in this, basically this design here, What we thought that was from was these MIPI cables are essentially running on the bottom side of this GPU. There's this crazy large header here, capacitors, resistors, whatever on the bottom of this board, and we thought that that was having some interference on the signal. So what we essentially added was this guy right here around the switching converter. So that would basically protect the MIPI signal from the switching converter. Hopefully, we have had a positive impact using this board over the other board, so I'm going to just assume that that was this change that we made here. Kept the serial port. It's now on the bottom side, right under this HDMI. We'll get a second view of it, and you can see the serial port later. And then, yeah, yet to have signal issues with the new stack. Okay, moving on to what we got rid of, because we got rid of a ton of stuff to make it into this smaller package. By the way, that serial port is right there. Okay, CAN breakout. We never really use this. We started using Ethernet instead of CAN to communicate with the Orin. We were always using Ethernet, but CAN was just a secondary option to communicate with our IMU that we used. But now we're using an off-the-shelf IMU that goes directly on one of our two main CAN buses. So we just no longer had the need for that, and that is a big connector space. Like as you can see here, we don't really have connector real estate. Maybe right here in between the Ethernet port, but this is nothing. This is a connector right here. You can't see it. Connector, connector, connector. Basically no space here. We also, swapped to an off-the-shelf IMU, as I mentioned previously. Fan controller, cool. We ran tests. You can see this right here. You can't tell the numbers, but trust me when I say that we ran tests running it at basically max power, and we never had any overheating issues. So we just got rid of the fan controller. We decided that we never needed to run an aux fan compared to the one that's this right here. This is the only fan we needed to keep it cool. Got rid of that. That saves a lot of space. And then finally the LEDs. This was kind of a hard change. We still have a couple LEDs. You can see two here and then two here that actually weren't soldered. But essentially, I talked to the software team and we never really use them. We don't really have the board real estate to put them anywhere. The only place we could put LEDs is these two for reverse voltage, and we have these two for MIPI, but they're not soldered. This was kind of a hard change, but it generally wasn't possible. And also interfering with this 40-pin header is just more software that we have to deal with, which we don't want to do. Okay, pros and cons of old versus new. Pros, smaller package, about half the size. This basically would have a second board about this size, so it would be, essentially half the size of what it used to be. Lighter, I'm not sure how much lighter, but it's definitely lighter. Better signal integrity. Sleep button, I'm not sure if we'll ever need that, but it's there if we do. DC to DC conversion. We added more output and input caps than we used to have, so this technically should give us better voltage flow. We kept serial, so we can keep on developing on that. Got rid of everything we didn't need, the LEDs, fan controller, CAN, stuff like that. And then better debugging. We have a lot of test points here for a 40-pin in case we ever want to do anything with it. And then we have a ground clip right here for using an oscilloscope. This is not connected to ground usually, but if you short these two pins right here, it will connect this to ground. And I find things like this on boards are really useful. Okay, moving on to cons. Input power gauge is really small now. As you can see here, I think this is basically you have to use 18 or 20 gauge versus before we were using a more Wago style connector and you could use basically any gauge that wasn't too big. Now we basically have to use one specific gauge. No longer indicating LEDs. We never really use them that much, so not a big con. And then case is, it says no longer designed. It's been designed since then. However, we haven't printed it yet because we ran into printing issues. I think that's basically it from my part. I'm going to hand it over to Charlie.
All right, thank you. So the pros of Orin's on the software side is that it's the most powerful coprocessor in FRC right now. It has 117 TOPS, 8 gigabytes of RAM, a deep learning accelerator, and a GPU. And also it offers us a lot of flexibility on the software side. For example, we can do whatever we want on the Orin. We could choose any camera we want or any software stack we want. Okay, and the first thing I'm going to talk about is how to flash an Orin. So the first thing you need to do is to use NVIDIA's SDK manager. What it does is that it flashes an Ubuntu-based image onto the Orin. And then once it flashes the base image, you need to connect it with a USB-C in order to the second part of the Flash, where it installs a bunch of developer libraries. However, only certain laptops are compatible with NVIDIA's SDK manager. Right now, we have a Xiaomi laptop running Ubuntu 22.04 to flash our Orins right now. And usually what I do when flashing it is that I select every developer tool available because it can't hurt. And after I finish using the NVIDIA's SDK manager, I use this GitHub repo to install OpenCV and a bunch of convenient tools. For example, NeoVim, ZSH auto suggestions, and much more. And after we do that, we need to install the IMX296 driver. The camera we use, the IMX296, is not natively supported by NVIDIA's Jetson, which means that we need to bring our own driver along with it. And this means that we need a custom device tree and a driver in order to use the camera. And to do this, we rebuild the entire Linux kernel with the driver and device tree file. And after we reboot, we start the driver with a sudo insmod. And the IMX296 MIPI camera isn't the only camera we need to use. For example, we can use the Intel RealSense camera, which is a USB camera that gives us color image data, and in addition to that, it also gives us depth estimation. Also, we could also use OV9281 with either serial or with either MIPI or USB, and this is a pretty good camera sensor, and it's what Limelights use. And finally, if we don't want to use MIPI anymore, we could always switch back to IMX296 USB cameras, and they're basically easier to work with than MIPI IMX296 cameras. And some additional setup tips is that when you're building the kernel in OpenCV, I recommend you to set the power to max send mode, which basically makes it build faster probably. And also, if you want to install a browser on the Orin, you cannot use snapped or apt, and you have to use Flatpak because of some permission issues. And finally, you should run sudo jetson clock /fan to start the fan to be max speed, just in case it overheats, but it probably won't anyway. And after you finish setting all this up, you could finally install Photon Vision on the Orin. So Photon Vision is our current software stack, but that may change soon. It uses GPU apotype detection that we took from Team 4143. And to set it up, you basically need to build the .so file and then use JNI so that Photon Vision can run the C++ code. And in order to support the IMX296, we needed to rebuild OpenCV, because by default, their OpenCV does not support GStreamer, which is required to read from the IMX296 drivers. And we also use JNI without OpenCV in order to read from the cameras. And finally, on their website, they support intrinsic calibration and easily disabling and enabling the cameras in case one doesn't work suddenly, so we have to disable it. However, there are some problems with Photon Vision. The first was that the code was overly complicated for what we wanted to do. Java JNI is really annoying to work with, in my opinion, and they had a bunch of pipelines and stuff like SQL databases, and that was just really annoying to work with. And the most important one was that we could not push to GitHub easily, because when we cannot build the code locally, we must build the code on the Orin. And in order to push to GitHub, we need access to Wi-Fi. But usually the Orin is connected to the robot, so we can't really connect the robot to Wi-Fi during a match or during drive practice. So we didn't have a good version control system. And that was really annoying for us. And also, we have this thing called Clonezilla, which is basically a fast way to set up an Orin. So what it is that it can save an SSD onto a computer, and then when we need it, it will put all the information of the SSD back onto the original SSD. So it is an operating system, so the laptop must be able to boot from USB. I think they have a version where it's Ubuntu-based or Debian-based. And it could, quickly be used to flash an NVIDIA Jetson Orin. So you don't need to build the driver or build OpenCV from scratch every single time you want to get a new Orin setup. So to use it, you first would image a USB with a Clonezilla ISO, and then you would take your SSD and then put it on the M.2 adapter, which is that one right there. And then you would boot your laptop into Clonezilla, and finally you would select your settings, and you could start either saving the SSD into your laptop or using the saved SSD and putting that onto a new SSD. Okay, and our new software stack, which is called BOS. So BOS is a completely custom C++ stack, and since Photon Vision uses like C++ code under the hood with JNI under the hood anyway, we decided to just like not use Java and just only do C++. So what it can do right now is that it sends network. Yeah. And a closer look at the source folder. So the calibration folder takes care of all the intrinsics and extrinsics. Hold on, someone's calling me, I think. C plus YOLO fairly quickly, and it is still being developed right now. So the structure of BOS is that we have a build folder, and it contains all the binaries which we later rsync or upload onto the Orin on the robot. We have our intrinsics and extrinsics in this constants folder, and in this folder, it just stores the intrinsics and extrinsics. And we also upload these constants onto the Orin. And then we have a Docker container with all of the dependencies required, so that like if you want to work on the Orin, you could just write code and build inside this Docker container with all the dependencies already there. And the main or source folder has all of our source files that that contains all the code for BOS. And then the scripts are basically a bunch of utility scripts that make building, deploying to the robot like a lot easier. And finally, third party has a lot of dependencies like Austin's GPU April type detector, a simple JSON library for intrinsics, and a comment filter. So here's a closer look at BOS's source files. So first we have calibration, which takes care of the intrinsics, extrinsics calibration. And then we have a camera folder, which basically is an interface for us to read frames from the IMX296 camera. And then we have our main code, which has the April detection using the GPU, pose estimation, and the part of the code that sends network tables to the Rio. And the Docker container, what it essentially does is that it first is based off of NVIDIA's official L4T Jetpack 36 Docker image. And then on top of it, it installs some basic dependencies, installs OpenCV, and then installs all WPIlib, which are all dependencies of BOS. So getting started with BOS, and I think I'm going to do a demo for this one. Oh, and also, like basically all these instructions are also in the slides, but I think it'll be better if I did a demonstration. Okay, so the first thing you would want to do is that you would want to pull the Docker container from our GitHub. So you would do docker pull this, and I'm not going to run it because I already have the container pulled on my computer. And after that, you want to start the container by doing sudo docker run, and it will require your password. Okay, and now after I do docker run, I am now in the Docker container with all of the dependencies. So from here, you would want to do ghauth login to initialize your GitHub. And the settings you would want to do is you would select github.com, SSH, enter, which is yes, and enter a passphrase, which I usually don't have one, so I just press enter again. And it will ask you how you want to log into your GitHub account. And I do web browser, and then I copy this code, and then I hit enter, and it would automatically bring me to a sign-in page that I can use. And after you do that, you would just simply clone BOS into your GitHub repository by clicking I'm going to use HTTPS for now, but you should use SSH. You would do git clone this. And then you could cd into it, and you have all the files. And then you would run the script /build.sh. Yeah, and it's downloading the dependencies, like Millihunt JSON third party, which is the JSON library. Okay, and it builds starts building automatically. And yeah, that's basically how you build BOS. I'm gonna stop it because it takes too long. Okay, and for what code editor you can use, you could either use VS Code, and to use it, you would need to install the dev containers extension, and then click the bottom left icon, and then click attach to a running container, and you would want to select the Orin container. And or if you want to use NeoVim, you could just like clone the config into this folder. And for example, this is how I clone my NeoVim config. Yeah, pretty simple. And future work with BOS, like what do we want to do in the future? So first we want to do is game piece detection. One of the main reasons Orins are great is because they have really good machine learning inference capabilities. Their DLA, Deep Learning Accelerator, can run inference extremely quickly and efficiently. And TensorRT is NVIDIA's provided API that we use in order to run neural networks on the Orin. And like some uses for it is that we could use ground intake during autos, detecting when resource filled maybe. And there's already an implementation of this in photon vision, so I just copied the code over. And cross-compiling. Right now, the Docker container technically supports x86 64 through emulation. However, when I tried to build BOS while emulating on my laptop, it was extremely slow. So that's not great. However, we could do cross-compiling with x86 64 instead, which would be a lot faster. To do that, we would need to do quite a lot of things. Like we need to copy the libraries from the Orin over into the sysroot so that when compiling, it would have all the dependencies available. And the two main ways we can do this is either with Bazel, which is a build tool that is very advanced and made by Google, or CMake, which is the extremely common tool, but it's a lot simpler. So another thing we could maybe do with Orins is path planning, although I'm not too sure if we could get it to actually work. So essentially what we want to do is that we want to kind of PID to a position while avoiding the reef. So how I thought we should do it is perhaps we run a A*/Dijkstra to find the shortest path. And then we'd fit a cubic spline onto the set of points where it would change its direction. And to fit a cubic spline, there are actually two ways to do it. We could either use a closed form solution, which is O of 1 time complexity, or the gradient descent, which is like probably not O of 1, but O of n time complexity. However, I think there's probably an easier way to do this to what I'm going to show you now. So the closed form solution is we have time, which is our input variable, and since it's a cubic spline, it would be t cubed, t squared, t1, and t to the 0, which is basically just 1. And our position would be either the x or y coordinate of our path. And for A is our spline basis matrix, and it is unique to every type of spline. For example, a hermetic spline does not have the same basis matrix as a B-spline. And finally, W are the things that we're trying to solve for through the closed form solution. And they have 4 control points for a given B-spline. And to solve for it, we would probably want to do something similar to linear regression's closed form solution, where we want to minimize the square of our actual position and our predicted position with the B-spline. And the prediction function, which is S of x, would be TAW, where W are the weights that we control. This is the spline's basics matrix, and these are our input variables. And to solve for it, we would first do our loss function, which is y minus TAW squared. We would expand it, and then we would combine like terms, and then finally we would solve for the gradient. And as you all know, when the gradient of a function is 0, that's when it's at its minima. So we would try to solve for 0 for it. And what we do is do some matrix algebra, and we finally would get W equals this to the inverse, and then multiply by YT/TA. And yeah, that's how I think we might be able to do it, but I'm not very sure if this is the correct way to do it. Yeah. Oh, and the limitations. Right now, this is only one spline, so it's technically C infinity continuous, but that spline might not be complex enough for like our given path. Maybe we need to like do crazy turns, and this spline probably can't handle it. So the way we fix that is that we add knots, and basically that means adding more control points, so more knobs that we can tune in the spline to make it do more complex stuff. And also, when we do this, we should probably use a B-spline for continuous acceleration. And finally, another problem is overfitting, which could be a problem, but I doubt it. And to do that, we could just simply add a regularization factor. A regularization factor, L1 or L2 regularization, and it should be pretty simple. We just need to add that term and then take the derivative of it. And this is modeled after scikit-learn SPLL prep, which basically fits a B-spline onto a set of points. Yeah, and this is where my inspiration for this algorithm came from. That's my presentation. Thank you.